Okay, so hi everybody, I'm Sara Faggi. I'm a postdoctoral researcher at NASA Goddard and research assistant at American University. And I'm gonna show you today how comets are interesting and cometary composition can be a niche science for Keck and NIRSPEC Keck especially. Okay, so when we talk about comets, we have to remember that cometary ices, of course, experience during their entire lives different processing, and starting from the origin in the interstellar medium, so the interstellar heritage, so all the freeze out, deuteration, and all this processing that in some way left some heritage signature in all the comets. And then going to the formation during the disk, the protoplanetary disk, these embryos, these cometary embryos, retain in some way processing from the photochemistry, the radial mixing, the thermochemistry, and according to the different birth location on the disk, of course, they experience different processing. And so this processing left a different signature in cometary ices. And of course, then once relocated in their current reservoirs, the Oort cloud and the Kuiper belt, they experience what we call the storage, so the cryogenic preservation, so mostly cosmic ray bombardment and UV radiation bombardment. And then when they are, since they're coming from these two different reservoirs, they experience a different evolutionary history. And these also can leave some signature in their eyes. Like, for example, short period comet experience thermal processing history that is going to affect their hypervolatile composition more than for Oort cloud comets. And so one of the questions that we ask is, how can we actually test the cosmogonic origin of this object? And so the answer of this is through studies of cosmogonic indicators, so sort of parameters that remain fixed in time, they don't change in time. And so those are the mixing ratio, the composition. So for example, abundances of a certain species relative to water, which is usually historically taken as baseline. Isotopic composition, so the Overage, for example, in water, and isomeric ratio, so Oort and para ratio in water in comets. And so basically, when we look at these different cosmogonic indicators, what we actually gain from the retrieval of this parameter in some way gives us an information of the process that these ices experience. For example, a very rich, hyper volatile ices comet, it might be formed in a very cold temperature where all the processing of isogenation, addition of grain surface plays a role in increasing the organic complexity, for example. Okay, so what we need to study this kind of isotopic, this kind of cosmogonic indicator in comets are summarized in the following slide. So we need the following key capabilities for such science. And the first is we need a wavelength range between 2.8 to 5 micron. And why? Because in region specifically, we have target all the sweet molecules together with water. So we target the hydrocarbons, we target the nitrogen species together with water and CO. And of course, if you look at the panel on the left, you can see that together with water, we have a lot of organic species going from 0.7 also beyond 5 microns. But observing from ground, we have to consider the background noise source of our observations. So basically from the ground, if we go beyond 5 micron, we are completely, of course, we cannot observe from there. We are background limited by the telescope and the atmosphere. So what we need is staying between the 2.5 and 5 micron, which is a sweet spot for observing from ground. And of course, NIRSPEC can provide that wavelength range. And then we need high resolution spectroscopy. So we need a resolution at higher than 20,000 to be able to do molecular isotopic investigation. And this kind of instrumentation is too bulky to go to space. So an instrument like NIRSPEC, of course, is going to still be very competitive also in the future. And we need the inclusion of long slit. And I'm going to show you a couple of results about this in next slides. Of course, since we're talking about comets, we need non-sidereal guiding. We have to be able to follow this comet during their approach to the sun. So an instrument like NIRSPEC Keck is actually an instrument that can provide all these key capability for cometary and also planetary science. And as I already mentioned, it will remain competitive, even if we have new space assets coming online, as for example, JWST, because an instrument like JWST will not have the spectral resolution as NIRSPEC. And so, for example, all the isotopic investigation will in some way be hampered. And also, if you think about the big telescopes that are coming online in the future, like the ELTs, most of the instrument, the spectrometer on board of this telescope will stop roughly about 2.5 micron. And maybe there is only one instrument in the ELT in Chile that we're gonna go beyond 2.5 micron. And so the 3 to 5 micron will still be a very sweet key region for Keck. And so, as I'm saying, this is a strong niche for NIRSPEC Keck. Okay, so let's see what we have been doing so far. And this is just a snapshot of all the cometary science and that I'm reporting in the last decade with NIRSPEC Keck. Of course, there is much more, and I couldn't put everything in one slide, but I just try to summarize, a couple of very important papers. And so you can see there are different papers from 2011 to this year to 2021. And I'm gonna show you now the latest results that we had on comet Neowise last year. It was a spectacular comet. And so we try to observe this object since it was discovered in March. And so we target immediately to follow this object first with the IRTF, with iShell, and then with NIRSPEC Keck. And we got two DDT nights. And this was actually a work that we did together with Caltech. And so we basically followed the comet with different multiple nights. And we just to show you this on the right, you can see spectra extracted from the KL band of NIRSPEC, order 23, and you can see beautiful emission of ethane, methanol, and methane. And just to let you understand how powerful this instrument is and how it can be still, as I'm telling you, competitive in the future, the same signal to noise that we obtained with Keck in 10 minutes of observing time on source, we needed 1 hour on source with iShell and IRTF. So that lets you understand how we can be more efficient, of course, with the 10-meter telescope at Keck. So we observed this comet during the approach to the sun and after the perihelion passage. And in this next slide, I'm going to show you one of the first results that we obtained, which is very important, and is about having a long slit. Because basically what we extract, one of the first results, was information about the spatial profile on this comet. So basically what we do is extracting the profile along the slit, as you can see here in this panel on the bottom left. Of the line, we try to understand how the gas and the dust are distributed. And that gives information about how the volatiles are released from the nuclei. And so what we actually observed very interestingly in this object, it was that the gas was shifted relative to the dust that are in this plot centered in the nucleocentered position towards the anti-sun direction. So the sun was in this side of the dust, so the gas was shifted in the anti-sunward direction. And the dust was actually a little bit enhanced in the sunward direction. And that changed with time because that happened in the first 3 observing nights. I'm showing you here actually 3 molecules. We detected 12 species, but I couldn't overwhelm you with all these plots. So I just choose 3 molecules, and I'm gonna show you the same results were for all the other 9 species. So basically, we observed this shift in the first 3 nights, and then the profile started to be again consistent, the gas with the dust. So they were symmetric. And so the first thing that we could learn with this analysis was that actually this was an indication of basically carried in the coma that then sublimate there, you know, and release the gas that we actually are observing. So these shifts were very interesting. Was one of the first shift that we actually have been observing in a comet so intensely. We have been observing shift gas between dust in other comets, but these were very enhanced. And so that was the indication of, as I'm saying, of a jet, of a possible jet of materia in that direction. If we put this together with the composition that we have been obtaining in this comet, we actually learn something more, because we have been seeing that the molecular mixing ratios, so the abundances of methanol, ethane, and methane relative to water in this comet changed dramatically from being depleted in the first stage of the observation to be almost enriched relative to a median value in the whole population of 24 comets that we actually have in our database. So what we have been learning is actually that this comet might have an heterogenic nuclei composition. So it means that, you know, the nucleus is composed by the aggregation of these pre-Umbrios cometary ices, and it might be that what we are seeing is actually a jet of material that it's chemically different or chemically experience a different processing relative to the other nucleus, the other part of the nucleus. And so we're seeing these changing in the molecular composition, and together with the information of the spatial profile, we could understand that the release of probably this part of the nucleus was different, chemically different. And so that was adding an additional, you know, piece of our puzzle in which we could try to understand what's the meaning of being depleted and being enriched. And the meaning is simply that we're seeing ices that experience different processing. So maybe the ices they were depleted, probably were depleted because either CO was depleted, and so because ethane and methanol can come from the hydrogenation reaction on grain surface from CO ices, not that freeze out. So basically, if we see a depleted methanol, most likely it can be because CO was depleted itself, or because we were in a warm temperature ambient where CO was not able to freeze out on grain surfaces. So we have these two information, but also when we see that methanol is enriched, we might think that those kind of ices actually form in a very low temperature ambient, where indeed CO could freeze out on grain surfaces and then lead probably to methanol. So we have this kind of information, and we put them all together in this puzzle, trying to understand the origin of this object and the evolution of the early solar system. One other very interesting results, which is still preliminary, while the other results are now in press in the Astronomical Journal, this is just preliminary, is the Overage water that we could in some way extract on this comet. We only have an upper limit, but it's a very significant upper limit, because basically the whole idea of studying the Overage water in comets is try to understand if comets deliver the water that we have today in our planet or not. And so basically what we have been observing so far in a sample of roughly 14, 15 comets is that the Overage in Oort cloud comet is usually higher, a factor of 2 relative to the reference value for Earth, which is in this plot, the orange line, horizontal line. So you can see the Oort cloud sample is all factor of 2 higher, while the Kuiper belt, so the Jupiter family comet, the periodic comet, has a value that approach the Vismo value, so the reference for Earth. Of course, the sample is 3 comet, and we need to have more points and more statistics to understand. But the fact that after Comet Lovejoy, which one measurement showed a very low Overage, and now Comet Neowise that show a very low upper limit consistent with the Vismo value, reopen the scenario. And so that's the need of an instrument like NIRSPEC on a telescope with such a big collective area as Keck, for this kind of investigation, because we can push the sensitivities and the detectability of this kind of investigation. So just to go to my final results, final slide. And so I'm gonna just quickly tell you about the future step.
I'm sorry, we're running, we have 10 seconds.
Okay, sorry, I'm gonna just go to the conclusion. So basically, we can investigate cometary abundances in isotope. We with NIRSPEC, we can get this observation with the very lower requirement in time relative to other facilities. And for far object and faint object and centaurs, which are actually the new targets for also the decadal, we need this kind of instrumentation on a telescope like Keck. Thank you. I'm sorry if I was a little bit longer.